Welcome to Octagon Math. In today's problem, we have three circles sitting inside one bigger circle. This small circle is tangent to the outer circle and this middle circle. This middle circle is tangent to the small circle and the bigger circle, and the bigger circle is tangent to this middle circle and the outermost circle. We are not given the radii of any of these circles. The only thing that we know is that there's a common tangent between these three inner circles and that the length of the tangent is 4 centimeters between these two circles and 2 centimeters between these two circles. And we are asked to find out the area of this colored region. Pause the video here to solve this on your own, and I promise you will find this very interesting. Alright, so the first thing to notice is that if these circles are tangent to each other, their common tangent will be vertical, and this line will pass through the centers of all of the 4 circles. So our strategy here will be to first find out the area of the outermost circle, then subtract the area of the inner circles from it, and then divide that by 2 to get the same shape of whose area we want to find. Since radius is the most important dimension to find the area of any circle, let's say that the radius of this circle is r1, the radius of this middle circle is r2, and the radius of the smallest circle is r3. Now, since the diameter of the outermost circle is the sum of the diameters of the 3 inner circles, the radius of the outermost circle is also going to be the sum of the radius of the 3 inner circles. So let's write it like this. The radius of this whole figure is going to be r1 plus r2 plus r3, which means that this area is going to be pi times r1 plus r2 plus r3 whole squared. Let's expand this, and this becomes r1 squared plus r2 squared plus r3 squared plus 2 times r1 r2 plus 2 times r2 r3 plus 2 times r1 r3. The next thing we want to do is to subtract the area of the inner circles from this. So let's subtract pi times r1 squared plus r2 squared plus r3 squared. Notice that if you open this bracket, you get pi r1 squared plus pi r2 squared plus pi r3 squared, and we are subtracting this whole thing from this equation. So this is very nice because these three terms will cancel out with these three terms, and we will get pi times 2r1 r2 plus 2r2 r3 plus 2r1 r3. Now, since each of these three terms has 2 as a common factor, we can take this outside the bracket to get 2 pi times r1 r2 plus r2 r3 plus r1 r3. Now the area we want to find is half this area, so let's divide this by 2, and we get the area that we want to find is equal to pi times r1 r2 plus r2 r3 plus r1 r3. So our problem has now reduced to find the value of this term. Note that we have 3 variables here, r1, r2 and r3. So we need 3 independent equations to find their value. Independent basically means that each equation should give you some new information. This is very useful to keep in mind when solving any system of equations, because sometimes you end up with 2 equations which are telling you the same thing, and when you try to solve them, things get cancelled out from both sides and you end up with some kind of identity like 2 equals to 2 or 0 equals to 0. Alright, so I want to make use of this 4 centimeter somehow in our equations. So let's draw a radius from the center of this circle to this point on the tangent, and we know that this radius is going to be perpendicular to the tangent. Let's do the same thing for this circle, and again the same thing for this circle. Now let's flip this radius over to this side and draw another radius here to make 2 quadrilaterals. Now since this is a common tangent, all the radii are going to be perpendicular to it, and therefore they are going to be parallel to each other. So if I draw another line here passing through this point, which is parallel to this line, we will get a parallelogram. So the bottom side of the parallelogram will be r1 plus r2, and the top side will also be r1 plus r2, and this side of the parallelogram will be equal to this side, which is r2. And the length of the remaining line segment will be r1 minus this r2, so that's r1 minus r2. Now what I actually want to focus on is this triangle here, because I want to make use of this information that the length of this tangent is 4 centimeter. We can do the same thing on this quadrilateral, and let's create another parallelogram. The bottom side of this parallelogram is going to be r2 plus r3. That means the top side is also r2 plus r3, and this side is going to be the same as this side, which is r3. Now the remaining line segment is r2 minus r3. So again, we have one more right angle triangle whose one of the sides is 2 centimeters. Let's clean this up a bit and focus on these two triangles. Now, both are right angle triangles, and this line is the hypotenuse of the first triangle, and this line is the hypotenuse for the second triangle. So we can apply the Pythagorean equation here and say that r1 plus r2 squared is equals to r1 minus r2 squared plus 4 squared. Let's call that equation number 1. Similarly, for the second triangle, we can say that r2 plus r3 squared is equals to r2 minus r3 squared plus 2 squared. Let's call that equation number 2. Notice that I am not writing the units here. I'll put them back when we are done solving. Now, how do we get our third equation? We have already made use of the fact that this line segment is 4 cm and that this line segment is 2 cm. What we have not made use of so far is that these two line segments are the same line segments. If we can represent that in an equation, we can get the third equation that is independent of the first two equations. Now, because this line segment is parallel to this line segment, one way to say that this line segment and this line segment are part of the same line or the same common tangent is by saying that these two angles are going to be the same angles. Now, once you are at this point, you can say that these two triangles are similar because both are right angle triangles and both have one angle the same. And that means that the ratio of their sides are going to be the same. Let's write that down as r1 minus r2 divided by 4 is equals to r2 minus r3 divided by 2. Now, if you were to take the ratio of any other two sides, you would end up with another equation which looks different, but basically is capturing the same information as this equation, which is that these two triangles are similar. That means that that equation and this equation will be linearly dependent. Okay, I have labeled this equation as equation number 3, and now we can get rid of this figure and solve to find the value of pi times r1 r2 plus r2 r3 plus r1 r3. Alright, we are almost halfway there. Let's start with the first equation. Let's first expand this term to get r1 squared plus r2 squared plus 2 times r1 r2. Then let's expand this term to get r1 squared plus r2 squared minus 2 times r1 r2. Now we can subtract r1 squared and r2 squared from both sides to get 2 times r1 r2 equals minus 2 times r1 r2 plus 4 squared. Now I want to get rid of this r1 r2 term from here, so I will add 2 times r1 r2 on both sides to get 4 times r1 r2 equals to 4 squared, which is 4 times r1 r2 equals to 16, which gives us r1 r2 equals to 16 by 4, which is 4. Notice that this already gives us the first term here. Okay, let's flip this back and get the second equation in the playground. Let's expand the first term here to get r2 squared plus r3 squared plus 2 times r2 r3. Now let's expand this term to get r2 squared plus r3 squared minus 2 times r2 r3. Similar to before, we can now subtract r2 squared and r3 squared from both sides to get 2 times r2 r3 equals to minus 2 times r2 r3 plus 2 squared. Again, I want to get rid of this r2 r3 term from here, so we'll add 2 r2 r3 on both sides and we get 4 times r2 r3 equals to 2 squared, which is 4. Now we can divide this equation on both sides by 4 to get r2 r3 equals to 4 divided by 4, which is 1. Note that this directly gives us the value of the second term in our final answer. Okay, let's flip this back and start working on the third equation. To solve this, we can cross multiply and get the 2 on this side and this denominator on this side, and we get 2 times r1 minus r2 equals to 4 times r2 minus r3. Let's expand these to get 2 times r1 minus 2 times r2 is equals to 4 times r2 minus 4 times r3. Let's add 2 times r2 to both sides to collect r2 on this side, and we get 2 times r1 equals to 6 times r2 minus 4 times r3. And we get 2r1 equals to 6r2 minus 4r3. Let's get this r3 on this side by adding 4r3 on both sides. So we get 2r1 plus 4r3 equals to 6r2. How can we further simplify this? Well, notice that we already know the value of r1 times r2 and r2 times r3. So if we multiply this equation on both sides by r2, we will get 2 times r1 r2 plus 4 times r2 r3 equals to 6 times r2 squared. Now we can directly plug in the values of r1 r2 and r2 r3 to get 2 times 4 plus 4 times 1 equals to 6 R2 squared, which means 8 plus 4 equals to 6 times R2 squared, which means 6 R2 squared equals to 12. And that means R2 squared equals to 2. Now, because the third equation had a different form, we didn't get the value of the third term directly. So what can we do to get the value of R1 times R3? Well, notice that we have an R1 here and an R3 here. So if we multiply the first equation and the second equation together, we get R1 times R2 times R2 times R3 is equals to 4 times 1. This is starting to look promising. This middle term becomes R2 squared, and we already know the value of R2 squared is 2. So let's plug that in, and we get R1 times 2 times R3 equals to 4, which means R1 times R3 equals to 4 by 2, which is 2. Okay, that was fun. Let's call this equation number 4, and we are ready to plug the values of all these three variables in our final solution. We know that R1 times R2 is 4, R2 times R3 is 1, and R1 times R3 is 2. So we get pi times 4 plus 1 plus 2. That gives us pi times 7. Now let's put back the unit for area, and we get 7 pi centimeters squared. So the area of this red colored region is 7 pi centimeters squared, and that is our final answer.